So welcome to the third day of our workshop, and this is the final day for our pedagogical lectures also, and we'll be starting technical lectures from this morning itself. So Professor Yacine Ali Haimoud will be finishing his second lecture, and that is a part of the last lecture of the four lectures on the primordial black hole. So Professor, you already know Professor Yacine Ali Haimoud is from New York University. So Yacine, please you take over.
Okay, can you all hear me?
Yes.
Okay, so I'll first finish yesterday's lecture on CMB limits on primordial black holes, and then we'll talk about gravitational waves. So just to summarize, we were on the limits on accreting primordial black holes, and the basic ideas, the basic steps are, first of all, to compute the accretion rate from primordial black holes accreting gas, then figure out with which efficiency they convert this accretion into a luminosity. Given this luminosity, this gives us a rate of energy injection per unit volume. So energy per unit time per unit volume, which is just the number density of primordial black holes times this luminosity. And this is proportional to the unknown fraction of dark matter in primordial black hole, this FPBH. And then the next step is to figure out how to convert from an energy which is injected into the plasma to an energy which is actually deposited into the plasma. Following this, one needs to compute the effect on cosmological recombination and then propagate this to CMB anisotropies and finally compare with CMB anisotropy data. So yesterday I talked about a little bit what goes into computing or estimating the accretion rate, namely some modification to the Bondi-Hoyle-Littleton accretion rate. And there are several complications. One of them might be that you could form an accretion disk. I also talked about how one can estimate some minimum physically plausible luminosity by saying that at the very least the gas will get heated up and thus radiates through free radiation. And this results from estimating this free luminosity. And again, this could be substantially different if you don't assume a spherical symmetric like accretion, but for example, if you assume the efficiency of a disk-like accretion, this could be substantially larger. And so I assume that Vivian Poulin talked about this yesterday, or might talk about it today. So the next step I didn't talk about yesterday was to convert from this energy being injected to an energy being deposited. And so this depends on what is the kind of particles that are injected and what are their kind of energies. So here, given that this is a free, we're assuming this free radiation, and the typical temperatures are correspond to 0.1 to 10 MeV or so. It turns out that the main channel that photons deposit their energy in the plasma is through Compton scattering, with either free or bound electrons. And when you account for this, you can compute the efficiency of deposition relative to the rate of energy injection. So if this number is 1, is when the energy is deposited on the spot. Whatever you inject, you also deposit it. But it tends to be less than 1 if there's a loss of efficiency in deposition versus injection. The fact that it goes above 1 is because the energy is not deposited immediately. So if you injected a large amount of energy earlier and then you normalize to the current rate of energy injection, you can also go above 1. So but the main point is that you have this loss of efficiency at low redshift because photons encounter fewer electrons. So once you have computed this rate of energy deposition, you can include this into the calculation of the recombination history, for example, with the code HiRec. So this includes a modification to the rate of recombination. And depending on the mass on the primordial black hole and depending on the abundance of dark matter of primordial black holes, the fraction of dark matter in the form of primordial black holes, this FPBH parameter, you get different redshift dependence for this change of the recombination history. This is then propagated into a CMB Boltzmann code. So the codes like class or CAMB are called Boltzmann codes. They solve the Boltzmann equation for CMB photons, and they require as one of their ingredients the recombination history. So this modification to the recombination history leads to modifications to the CMB temperature and polarization power spectra. I'm not showing it here, but there's also a change to the CMB cross power spectrum between temperature and polarization. And then finally, when you compare this with Planck data, this allows you to set an upper limit for every given primordial black hole mass on the fraction of dark matter in primordial black holes. And this is in the simplifying limiting case where primordial black holes all have the same mass. So these are the kind of upper limits you get as a function of primordial black hole mass, the maximum fraction of dark matter in primordial black holes. And as I was describing briefly yesterday, we have two, in this paper, we have two limiting regimes for the temperature profile close to an accreting black hole, this either photoionization case or collision ionization case. And you see that they differ by 2 orders of magnitude in FPBH. So this is to give you some order, some idea of how uncertain this calculation is. But this should be the most conservative limit. And so this tells you that above about 100 solar masses, primordial black holes cannot make all of the dark matter. They need to make some, they are constrained by CMB anisotropies to make a fraction less than 1 of the dark matter. Again, this is under some assumptions, some most conservative assumptions about the luminosity of the primordial black holes. But if you take less conservative assumptions, and if you assume that the efficiency of radiation is comparable to disk, what you obtain from a disk accretion disk, from an accretion disk, then you would get much stronger constraints. Though I would not call these constraints, but rather the potential reach. So if you were able to prove beyond reasonable doubt that the accretion must be disk-like, must have the same efficiency as a disk-like accretion, then you could reach much lower fractions. So this is these spherical accretion limits. And this is how low you could reach if it was a disk-like accretion. So to summarize this first lecture from yesterday, so as in the first part, I told you, I hopefully explained a little bit how you can use both the frequency spectrum of the CMB and the temperature and polarization anisotropy, so spatial or angular variations of the CMB. Both of them in different ways can probe energy injection in the early universe. This can be used, for example, to test annihilating dark matter or decaying dark matter in the early universe. Here we've applied this to primordial black holes. I've discussed 3 different mechanisms that can inject energy in the early universe. So first of all, what is shown in this illustration here is the dissipation, the silk damping of small-scale perturbations. So you start with some initial power spectrum, and then because of the finite mean free path of photons, this perturbations below some small scale gets damped. And this dissipation leads to heat. And so because of the limits from Kobe-Fairas, we have some upper limits on the primordial power spectrum corresponding to primordial black hole masses greater than about 2 times 10 to the 4 solar masses. So basically, Fairas rules out primordial black holes greater than about 20,000 solar masses, provided they are formed from the collapse of Gaussian primordial fluctuations. The second thing we discussed is Hawking evaporation, and this sets stringent bounds on primordial black holes, which are very, very light on the completely other end of the mass spectrum of order 10 to the 15 to 10 to the 17 grams. And lastly, I discussed accretion, limits from accreting primordial black holes, and this sets these limits for primordial black holes above about 100 solar masses, and these limits could be improved, could probably be significantly improved by understanding the accretion physics better. So before moving to lecture 2, I'll take questions on this first lecture, and then maybe we can move on to lecture 2. Were there any questions?
So yes, Yacine. So there is a question by Shopnil. The question is like disk accretion has width that is in your plot pink region, but spherical is widthless, just a line. In Vivian's plot, why is that?
Oh, this is just their choice. So this just means that above the line is ruled out, and they colored here to say like above this line here is ruled out for them. Yeah, this is just their choice. I don't know why they chose it this way, but yeah, this is also these lines mean the same thing. It means that whatever is above them is ruled out.
And Juan Garcia Bellido has a question that how are the constraints weakened if the fluctuations are non-Gaussian?
How the constraints weaken the fluctuations are non-Gaussian. So Juan probably knows this very well. So if the fluctuations are non-Gaussian, then even with a very small, so Kobe-Fires sets a limit on how large the primordial fluctuations can be. They have to be very small. So the variance has to be less than 10 to the minus 5. So if fluctuations are non-Gaussian, then even with an RMS with a variance of 10 minus 5, you could have a very long tail of large overdensities, and you could have a not negligibly small tail of perturbations of order tens of percent, which is what you need to form primordial black holes. So that's how these limits on PBHs are weakened. So these limits are only indirect limits. They're really limits that depend on some connection between primordial perturbations and primordial black holes.
Yes. There is one more question from Suchetana Chatterjee. His question is, what about the emission from the accretion disk? Does that affect anything?
Yeah, so this is exactly this. So the emission, this is exactly what we're talking about. Here, I was trying to estimate the emission or the luminosity from the spherical-ish accretion around the primordial black hole. But if you have an accretion disk, this emission or luminosity would be much larger than what we compute here. And so basically, you propagate this luminosity to the change of the free electron fraction. And so for the same PBH mass and PBH abundance, you would have a much larger effect if you had an accretion disk. And so you would have a much larger effect on the CMB power spectra. And as a consequence, you would have much stronger limits if it was an accretion disk. But if you want to be able to set a conservative limit, to say, I am 95% or 99% confident that primordial black holes above some given line are ruled out, that this fraction of primordial black holes is ruled out, you need to be confident with the same level of confidence that accretion indeed is disk-like. And this is, I think, difficult to prove to high confidence.
So if you like, there is one more question from Kanaya. He says, what is the ROM dashed line in the plot for the accretion-based constraints?
This plot was, so this is Riccozio, Stryker, and Mack. This was a previous paper of theirs from 2008. And this is to compare with our results. So there are some things which they did not do correctly. So they did not account for the correct relative velocities of baryons and dark matter. They also probably have some mistake in estimating the spectral distortion limits. So it turns out that the CMB anisotropy limits are much, much more constraining than spectral distortion limits. And they have also a much higher efficiency than what we estimate from free radiation. So again, it could be that primordial black holes are much more efficient radiators than, would be much more efficient radiators than what we assume. But if you want to set a robust constraint, you need to be absolutely certain of the minimum amount of luminosity of these primordial black holes. So yeah, this is a previous work, just to compare with our results.
Okay, Yacine, one more organizational point. Actually, I hand over to Professor Sriram Kumar to chair the rest of the session. So you please continue with the lecture now.
Okay.
Thank you.
So let's move to lecture 2 on gravitational waves, and we'll see how much we cover. So just like I did last time for the CMB, I will have two parts. As the first part, I will discuss the basics of gravitational waves to make sure everyone is on the same page and talk a little bit about observables. I will put some emphasis on pulsar timing arrays because you may have heard of recent hints, quote unquote, from a nanograph. So I will give you hopefully the tools to understand these. And then I will talk about how primordial black holes can be either directly or indirectly sources of gravitational waves and how one can extract constraints as a consequence. So the first part will be how they can generate gravitational waves, how the primordial perturbations can generate gravitational waves at second order. And then I will talk about the formation of binaries, either in the late universe or the early universe. So let's start with the basics of gravitational waves. So this cannot replace a GR lecture, but it will be a very quick summary. This is the space-time metric. A time nu is the Minkowski metric, -1, 1, 1, 1, diagonal. This h mu nu here, so to talk about gravitational waves in a meaningful way, we know how to do it when we have small perturbations around a flat space-time or around some background space-time. So this is small. We can decompose, so this has 10 independent components because it's symmetric. There are 6 linear combinations of these components, which are gauge invariant, which means that they are invariant under coordinate transformations. 2 of those are scalar, phi m psi. Those are basically the relativistic generalization of just the Newtonian potential. There's one so-called transverse vector, which is a divergence-free vector. This contains 2 independent components, so that takes us to 4. And then there's one transverse trace-free tensor mode, which totals 2 more independent components. So this TT means transverse trace-free. This is the trace-free condition. It's just that the trace, the sum over diagonal elements is 0. And this transverse means that the divergence on either index is also 0. And this HIJTT is the gravitational wave strain. It satisfies a wave equation, and it propagates at the speed of light. This is the ultra basics. Again, please go to a GR course to make sure this is understood deeper. Something that is a very useful, important formula to know for gravitational waves is the quadruple formula. So if you have some source of matter, this formula actually holds for a non-relativistic source of matter, a source of matter where things move at much less than the speed of light. This source of matter has a mass quadrupole moment. So this is basically of order m times r squared, where r is the typical distances between this typical scale, length scale of the source, and m is a typical mass. This will generate some gravitational waves at a distance little r away from the source, which is the double time derivative of this quadrupole moment, evaluated at retarded time. So we're going to work in geometric units where g, Newton's constant, is equal to 1, and c, the speed of light, is equal to 1. So masses and lengths have the same dimensions in these units. So this quadrupole moment has dimensions of mass cubed or length cubed, and times also have the same dimension. So when I take 2 derivatives, this gives me back just 1 dimension of mass, and when I divide by r, I get something which is dimensionless, as it should. Gravitational waves carry energy and momentum. They have an energy density which is proportional to the square of the time derivative of the gravitational wave strain. Again, this gives you something which has dimensions of 1 over length squared, which is the correct dimensions for an energy density. And they also carry some energy flux or momentum density, where you have 1 time derivative here and 1 gradient here, spatial gradient here. So by using, for example, the energy flux equation, by using the quadruple formula, you can compute the gravitational wave power radiated by a time-varying quadruple moment. And again, this is dimensionless in geometric units. And this quadruple moment, triple derivatives, is also dimensionless. So this is the equivalent of the electric dipole formula, but instead of electromagnetic waves, is for gravitational waves. So the power radiated is the square of the quadruple moment's third derivative And this average is over several wavelengths or several oscillation periods. All right. So just like electromagnetic waves can have arbitrary frequencies over a very broad range, just like the same thing holds true for gravitational waves, different frequencies will be generated by very different sources. In the case of gravitational waves, for example, frequencies around kilohertz are generated by the inspiral of solar mass or tens of solar mass black holes. And then as you go to larger black holes, you probe lower, they emit gravitational waves at lower frequencies. And in this nanohertz frequencies, you're probing, so here's the merger phase, but here you're probing the inspiral phase at even lower frequencies of supermassive black holes at the center of galaxies. And just like for electromagnetic waves, there are many different kind of instruments, from optical telescopes, gamma rays on the very high frequencies, optical, and then infrared and radio, etc. There are also multiple instruments that either already exist, such as LIGO and pulsar timing arrays. LIGO has detected gravitational waves, pulsar timing arrays are still searching for them, or instruments which are being planned, such as LISA. Okay. So briefly to recall how LIGO works, even though this is really not a sufficient explanation, but what gravitational waves do is that they create a deviation of neighboring geodesics. So if you have some test masses, which are initially separated by delta x, then and if there's a gravitational wave with strain hij, then their separation will have this perturbation, which is proportional to the strain times the original separation. So you've probably seen these kind of graphs. So if you put these tests, if you imagine test masses on a ring, as a gravitational wave passes, it will displace, it will create a relative displacement of these test masses according to this equation, which, say, in the case of a plane wave, which would be linearly polarized, it would look like this. It would look like a squishing. This circle would be distorted into an ellipse, and then into an ellipse in the perpendicular direction. So very heuristically, this is how LIGO or LISA works. Instead of test masses, you have mirrors, which are suspended in such a way that they're essentially test masses. And so if a gravitational wave passes, it will shorten one distance versus the other. And then you can measure this by interferometry. So you have probably heard of this because LIGO now has detected gravitational waves. But what you may not have heard much is how pulsar timing arrays work. So I want to spend a few minutes explaining this because I've been also working on this recently. So pulsars are neutron stars, so with radii of a few kilometers or maybe 10 kilometers, which are spinning very rapidly, and they have some strong magnetic fields whose axis may not be aligned with the spin axis, and this generates some radio emission, or in general electromagnetic wave emission. And if the Earth happens to be aligned with with the beam here of the radio emission, what you see is, as a function of time, you see pulses of radio intensity as the pulsar is spinning and acts like a lighthouse shining on the Earth. Okay, and this is, of course, not to scale. So,
Yacine, can I interrupt briefly with a question?
Yes, of course.
Sure. There is a question which says, if primordial singularities exist, then it suggests that the universe truly was born from a singularity itself. I don't know whether it is relevant, but there is a question that has come in. Maybe you can read me out.
I'm not sure how it relates to what was before. I'm sorry. Yeah, I'm not sure if I don't think I've talked about any singularities.
Okay, we can leave it there. And if there are some such questions, we can come back later. I'm sorry.
Right. So given these pulses from the pulsars, one can measure the times of arrivals, TOAs here, as a function of pulse number, put them on a graph like this. you can fit some smooth function to these times of arrival as a function of pulse number. This is called a timing model. So this accounts for the fact that, say, the pulsar is moving. It might even be accelerating. For example, if it's part of a binary, it will have some motion which will affect these arrival times and things like this. So it will also account for some deterministic spin down of the pulsar and things like this. So you fit some smooth timing model, and then you subtract this times of arrival minus this smooth model. And then what you get is what is called the time residual. So it's the time of arrival minus this smooth timing model. And presumably this is something which is now consistent with noise because you've subtracted some deterministic model. Just to give you an idea of how the real data looks like, this is from one pulsar from the nanograv that is monitored by the nanograv collaboration for 12.5 years. You see over this whole span from 2004 to 2018 almost. And so these different colors represent radio frequencies, different radio frequencies. And so you see that typically you have this microsecond precision error bars on the timing residuals. Okay, so now this timing residual, which is basically consistent with noise, consists of what? First of all, some intrinsic noise of the pulsar. The pulsar may have some sort of pulsar quakes or whatever, some physics which makes its rotation rate not exactly like a perfect clock. And in addition, there is some timing residual which is induced by the potential presence of gravitational waves. This, how does it look like? So this has dimensions of time. The gravitational wave strain is dimensionless. So this is actually going to be some sort of integral over time between the pulsar, which is at some distance dp, and Earth. And this p hat here is the direction of the pulsar. So you have to project this gravitational wave strain, which has two indices, twice on the direction of the pulsar. If you take the Fourier transform of this equation, so you can see this, even though this is a measured at discrete times, you can, if you have enough arrival times, you can see this is a continuous function. You can take its Fourier transform. So then what you get is this double projection of the gravitational wave strain, Fourier transform, divided by frequency, and you have some geometric factor. So this pulsar intrinsic noise is basically completely unknown, okay? Why is that? Because no one, as far as I know, has been able to take a pulsar and isolate it in a lab. So contrary to radio telescopes, where you can really characterize your noise by taking a receiver, putting it in a lab, or shining some sort of known thermal loads on your telescope and characterizing its response, pulsars are bathed in gravitational waves, and one cannot separate their intrinsic noise from the gravitational wave timing residual if we just look at a single pulsar on its own. So, however, this intrinsic noise is uncorrelated from one pulsar to another. So if you cross-correlate these intrinsic noise between two pulsars, it's something that we don't know if it's just P equal Q, but if P is different from Q, you get 0. Because two pulsars have different noise and have no reason to be correlated. So the only way to detect gravitational waves through pulsar timing is through the cross correlations of different pulsars. So this gravitational wave term here has some cross correlation between two pulsars, which one can compute exactly if you know some. So this HC is the so-called characteristic strain, is the characteristic amplitude of the gravitational wave strain at the frequency f. It's also dimensionless, the way it's defined. So if you assume, for example, that the energy flux of gravitational waves, if gravitational waves are stochastic and if their energy flux is isotropic, if you get the same power from every direction in the sky, then there is a very simple geometric dependence of this cross correlation, which is given by this Hellings and Downs function. So this was computed by Hellings and Downs in 1983. You can look up their paper to see exactly how it depends on this angle. And this angle is the angle in the sky between pulsar P and pulsar Q. So this is, again, if you have an isotropic gravitational wave background, but because this gravitational wave background, in the sense that it's isotropic in in intensity, but you will still have a different response if pulsars have different separations. And this response has a very well-known form. So again, the only way you can detect gravitational waves through pulsar timing arrays is through these cross correlations. Gravitational waves also do contribute to the autocorrelations, so of the timing residuals of each individual pulsars. But as I was saying before, this is completely degenerate with the completely unknown intrinsic noise of pulsars. So you can only use these autocorrelations to set upper limits on gravitational waves. And if you want to try and detect gravitational waves, you need to use cross correlations. So this is hopefully giving you a little bit of the tools to understand the nanograph 12.5-year results. If you haven't heard of them, you can just search this and find the results here. So here they're showing the posterior distribution of basically the log 10 of the characteristic gravitational wave strain at a frequency of 1 over a year. And the orange curve is measuring some kind of common noise process common to all pulsars. And this is peaked. But if you look at the cross correlations, which are sensitive to gravitational waves, you see that this is flat. So in other words, because there's no peak, significant peak in the blue PDF here in the cross correlations, there is no detection of gravitational waves. There's not even a hint of gravitational waves. This is a hint that the data analysis probably should be changed so that it doesn't produce, so some common noise doesn't produce something that could be attributed to gravitational waves.
Yacine, there is a question about the noise.
Okay.
It says, how do we know that the intrinsic noise won't be correlated? What does the noise arise due to?
So the idea is that this intrinsic noise means really that you have the pulsar. The pulsar is not spinning. So the idea is that if the pulsar spins perfectly regularly, like a perfect clock, then you don't have any noise. But if the pulsar, for some reason, will have some pulsar quakes or some, the rotation periods follows some random walk, or maybe the period derivative follows a random walk, then this will lead to a noise in these arrival times of the pulses. And now if you take two different pulsars and they both have pulsar quakes, there's no reason why this pulsar quake should have any correlation with one another. So that's why these intrinsic noise is uncorrelated. Now there can be other sources of correlated noise, which are not gravitational waves, which I didn't mention. So there could be, for example, the fact that you have you need to compare your times of arrival to some global time standard. So you need to use some global clock, which is super, super precise. And well, maybe, so this global clock is the same one for all pulsars. And so it could be that this clock itself is, has some irregularities, and in which case you will get the same irregularities in all the pulsars, and this would lead to also some correlated noise between pulsars. But its dependence on the angle will be different from what you expect from gravitational waves. And that's how you can distinguish between them. Any other questions? Okay.
There is none for now.
Okay, so basically what nanograph tells us is that there's some upper limit on the characteristic strain of gravitational waves at a frequency of about 1 over a year, which is less than 3 times 10 minus 15 or so. Okay, and we're going to use this later on. So we already asked about questions. And so let me move on to the application to primordial black holes. So we're going to right away talk about pulsar timing arrays. So first, just like we were talking about silk damping yesterday as a way to probe the primordial perturbation, here one can also probe the primordial perturbations. So not directly probe primordial black holes, but probe the perturbations that could have generated primordial black holes through gravitational waves. So what's the idea? Again, this h mu is our metric perturbation. We're going to expand it into some small book. So we're going to use some small bookkeeping parameter. And we're going to say there's some first order perturbation of order epsilon, and then some additional perturbation of order epsilon squared with superscript 2. Now, let's assume that at first order, we only have pure scalars. We only have these Newtonian potentials, phi and psi. So in particular, we don't have gravitational waves at first order. Okay. Now, if you write down the Einstein field equations, which are nonlinear, and then you expand them in this bookkeeping parameter epsilon, you will find some equation for the gravitational wave strain, which will be sourced by something on the right-hand side. The source is basically going to be quadratic in the gradients of these scalar potentials. And again, you can check that this has the right dimensions. This has dimensions of dimensionless divided by time squared, and this is dimensionless divided by time or length squared. So this piece here is what you would have if you had a pure wave equation, as I told you, gravitational waves follow a wave equation. And this piece with the h is the Hubble rates. This comes from the fact that this is really gravitational waves in an expanding universe. So now we're expanding about not a flat Minkowski background, but a Friedmann-Lemaitre Robertson-Walker metric. So in principle, you should, given some initial conditions, figure out how phi evolves in time, and then solve this linear equation given this source. And this is what several authors have done, but here we're going to do something, make a very simple order of magnitude estimate, which happens to give some decent answer. So just after horizon entry, this is when these Newtonian these potentials will start sourcing gravitational waves. And so just after horizon entry, the characteristic strain will be of order this Newtonian potential squared, which is also the primordial curvature squared. Zeta is the primordial curvature. Okay, now let's try to estimate what happens after horizon entry. So horizon entry is when the scale of a perturbation, the wavelength, is of order the Hubble radius. Gravitational waves, as I said earlier on, have some energy density which is proportional to h dot, the time derivative, squared. So if they have some frequency omega, this goes as omega squared h squared, if it's sinusoidal. As you know, in an expanding universe, wavelengths scale as the scale factor, proper wavelengths, and frequencies will scale as 1 over the scale factor. So this tells me that this energy density scales as 8 to the -2 times hc squared. Now, gravitational waves, and I'm using here I'm cheating a little bit. Normally, one should derive this first to obtain this, but here I'm going to say intuitively, because gravitational waves propagate at the speed of light, you can think of, they should behave like radiation. And so in the absence of sourcing, of creating new gravitational waves, their energy density should decay just like that of radiation as 1 over scale factor to the 4th. And as a consequence, if I plug this in, I should have that the strain decays as 1 over the scale factor. So if I combine this and this, I should find that the characteristic strain at some given wave number k is the primordial curvature fluctuation at that wave number roughly, or half that wave number, say, squared, times some dilution factor, the scale factor of horizon entry divided by the scale factor A. Now, we need to figure out what is the scale factor at horizon entry. So this is determined when the comoving wave number k is equal to the comoving horizon, inverse comoving horizon. And if you just plug in what is the Hubble rates during radiation domination, you will find that the scale factor at horizon entry is something like 10 to the -11 for comoving wave numbers of 1 inverse parsec. I'm using 1 inverse parsec because the comoving wave number, so a wavelength today of 1 parsec corresponds to a frequency basically of 1 over a year. It takes basically 1 year. It's like 3 light years. 1 parsec is 3 light years. So 1 parsec corresponds to frequencies of 1 inverse year, which is what pulsar time arrays probe. So if I now plug this equation into this and I ask what is the characteristic strain at scale factor 1, which is today, we find this 10 to minus 11. This tells me that zeta squared at k of 1 inverse parsec is less than 10 minus 4. And so zeta is less than about 10 minus 2. And if you do a much more, and you should do a much more involved calculations to do this precisely and to get the full curve, and this is what these people have done, and you can also look at this reference for other detailed calculations, you indeed find that around k of 10 to the 6 inverse megaparsec, so 1 inverse parsec, co-moving, your upper limit, so this is zeta, I should have said it, your upper limit on the primordial curvature perturbation is of order 10 minus 2. Now these curves are the upper limits that just the, say, upper bounds on the abundance of PBHs tell us, imply. Again, if PBHs were generated from the collapse of Gaussian density perturbations. But those limits are really just logarithmically sensitive on the upper limit on PBHs. So just by saying basically that the number density, the abundance of PBHs cannot be more than the dark matter abundance, which is just a very simple upper limit, doesn't require much work, you would get basically these these blue curves very close to those ones. So the fact that this doesn't go lower, okay, tells us that PTAs do not really put any pressure at the moment on PBHs as a dark matter candidate. Okay, they do not, contrary to spectral distortions, which sets a much stronger limits, pulsar timing arrays do not set a strong limit on sufficiently strong limit on primordial curvature perturbations, and do not rule out primordial black holes. But if you had a larger pulsar timing array, for example, by including the hundreds or even thousands of pulsars that SKA might find, then you could lower potentially this bound much lower. Are there any questions on this before I move to primordial black hole binaries?
There are no questions, Yacine, at this stage.
Okay. So let's talk about primordial black hole binaries, and probably Misao Sasaki will talk more about this. And I'm guessing that Antonio Riotto might also talk about these pulsar timing array things, but if not, you can also ask them. So two ways that so far have been thought of to produce primordial black hole binaries. And then here I'm going non-chronologically. So the first way was proposed by Bird et al. Paper I was also a co-author on in 2016. So here is the basic idea. I'm going to try to be very pedagogical about most of it. So if you have two masses, in this case primordial black holes, but it doesn't really matter if you have 2 point masses, which are on a nearly parabolic trajectory, they have some impact parameter b, some velocity at infinity v. You can estimate the closest approach at pericenter rp, and the velocity at pericenter vp, just by using conservation of angular momentum. So this is the angular momentum at infinity per unit mass. And by saying if it's a quasi-parabolic orbit, which has zero energy, this gives you the energy, the zero energy at pericenter. And so by combining those two, you can find what is the pericenter approach and the velocity at pericenter in terms of the mass and the impact parameter and velocity at infinity. You can estimate what is the time scale that these two objects pass at pericenter, which is the pericenter distance over the VP, and this gives you this ratio here. And again, every time you can check that this has the correct dimensions. If not, you should tell me. Then from this, you can estimate the mass quadrupole moment at pericenter, which again is m times the size of the system at pericenter, mRp squared. Then you can take its third derivative, take q triple dot is of order mRp squared over tp cubed. And the energy radiated, so the power radiated by gravitational waves is this q triple dot squared. And so the energy radiated will be q triple dot squared times the time of the interaction, which is again this time of pericenter passage. And if you plug everything here, you will get this m to the 8 over bv to the 7th power. Now, if there is more energy radiated than the original energy of the system, which is not quite 0, but it's of order mv squared, then the two masses, which originally were unbound, will become bound. They will have a negative energy after radiating some of it to gravitational waves. And if you ask what is the criteria, what this implies, it implies that your impact parameter is less than m over v to the 9/7. So from this one can derive a cross section, which is this, impact parameter squared. And so this gives you that the cross section for capture through gravitational wave radiation is of order m squared times v to the -18/7. So it's a very strange power law, but it's actually very easy to derive it by going through the steps I just highlighted. This was derived by Quillen and Shapiro in 1989. And just like I was telling you about the electric dipole formula, this is the analogous of free bound capture. If you have an electron and a proton, the electron can be captured by the proton by radiating electric dipole radiation. And there's some cross-section for this. All right, so now given this cross-section, if you now suppose that, in the present day universe, or at least in the recent universe, primordial black holes, just like the rest of dark matter, are part of halos. If we assume that we know their density, the halo density rho h, and if we assume that we know the typical halo velocity, vh, which we can estimate given the mass and density of the halo, you can compute the merger rate per halo, which is integrating sigma v times the number density of PBHs squared. And this gives you this scaling with the halo mass, the halo density, and the typical velocity dispersion in the halo. Now, from this, you can compute the total merger rate in the universe, so per unit volume. So this is a merger per unit time. And then here, if you multiply by the number density of halos per mass interval integrated over the mass interval, this gives you a merger rate per unit. So a rate of mergers per unit time, that's a rate per unit volume. This integral happens to diverge at small halo masses, but there's a natural cutoff because these halos, if they are made of discrete objects, they will evaporate, meaning that two-body interactions tend to, the two-body relaxation will tend to eject some bodies over time out of the halo. This is called the evaporation, and you can find more about it in the book by Binney and Tremaine, for example. And so there is some minimum cutoff for halos, some minimum mass that halos, for them to not have yet evaporated within a Hubble time. All right, so the last step is to say, okay, what is the typical halo density? Well, it's about 200 times as a rough order of magnitude, or a couple hundred times the mean density at the time at which the halo collapsed. So when the halo virializes, it virializes to about 200 times the current time density, and then it remains, more or less constant in time. And then this halo mass function you can use, for example, an approximation would be the pressure sector mass function, or you can try and use more sophisticated ones. So with all of these ingredients, you can compute this merger rate per unit volume. Both this rho h and this pressure sector require knowing the variance of fluctuation as a function of halo mass. So in Bird et al., what we did is we assumed the standard CDM power spectrum, which is measured on large scales, from CMB anisotropies, etc., and we just extrapolated it to small scales. But in reality, what we noticed, and we pointed out in this paper later on, is that, well, because primordial black holes are a discrete object, they will have a Poisson fluctuation, which will enhance the perturbation on small scales. So this will affect every single step of the calculation. It will really vastly change the merger rate per halo in terms of merger per year. So for a given mass, you have vastly higher merger rate per halo because these halos which collapse earlier are much denser. It will also change the time of evaporation, and so it will change the cutoff. So the cutoff that we had in the Bird et al. Paper was halos of a few hundred, something like 400 solar masses, which contain just like a dozen or so primordial black holes. But if you account for these Poisson fluctuations, the cutoff is more like halos of several tens of thousands of solar masses, which contain thousands of primordial black holes. And if you fold everything together, yes?
I'm sorry to interrupt. You have 10 minutes. Maybe if you can wind up about 5 minutes or so, we can leave a few minutes for questions.
Okay, I'll do that. Yeah. So basically, between these two things, in either case, you find a merger rate of about 1 per gigaparsec cube per year, which is somewhat lower, but within the order of magnitude approximation consistent with the merger rates inferred by LIGO. But that is if primordial black holes make all of the dark matter. Okay, the second channel to form binaries was pointed out by Nakamura et al. In 1997, and Misao Sasaki is one of the authors here, so perhaps he will talk about this more. So I'll just go over this very quickly. So the basic idea is that on very small scales, so on large scale, primordial black holes should follow the density, the adiabatic dark matter density fluctuation, but on small scales, they should be randomly distributed. If primordial black holes happen to be born in close pairs, they will decouple from the Hubble flow deep in the radiation era. So I'm not going to go over this calculation, but I will just say that you can estimate the scale factor at which a given pair will decouple. And from this, you can estimate the semi-major axis that this pair will have. And this depends on the comoving separation of the pair. And if you know the distribution, the probability distribution of comoving separation of the nearest neighbors, which is just from Poisson statistics, then you can compute the probability distribution of the initial semi-major axis. Then these pairs, instead of falling head-on onto one another, so this is my pair here, it gets torqued by neighboring primordial black holes. And again, given the distribution of the second nearest object, you can compute the distribution of angular momentum of the pair. And since the merger time depends on semi-major axis to the 4th power, angular momentum to the 7th power, reduced angular momentum to the 7th power, you can compute, given the distribution for semi-major axis and eccentricity, you can compute the merger time probability distribution, which is related to the merger rate. So if primordial black hole binaries are undisturbed between their formation and the time they merge, what you find is that if they make all of the dark matter, their merger rate is orders of magnitude larger than the upper bounds from LIGO. In other words, if PBH binaries are undisturbed between formation and merger, then LIGO would set very, very stringent constraints on their abundance. These are only potential limits because of this big if here. So what happens is that the primordial black hole binaries happen to start typically with a very small angular momentum. They're very highly eccentric, and as a consequence, it's very easy to torque them. And because the merger time scales as angular momentum to the 7th power, even a small torque could change the merger time, hence merger rates, by a lot. And so to figure out, so one thing that we want to figure out is whether they get significantly affected by other primordial black holes, these binaries. This has two aspects. One is the microphysics. If you have three bodies, what are the outcome of these interactions? And Karsten Jadamczyk will probably tell you about this. And the second aspect is that in what environment do these primordial black holes reside? And so this is something we're trying to address. We started looking into simulations of primordial black holes plus particle-like dark matter and see how structure forms in the early universe in these scenarios. And what you obtain is that as the primordial black hole fraction increases, Poisson fluctuations will lead to much larger structures at redshift as high as 100, where in the usual scenario, you would have no structures at all. So I'm done. Hopefully it's on time. The summary of this lecture is that I told you about pulsar timing arrays, which just like silk damping are a way to probe the primordial power spectrum, which can in principle set indirectly limits on primordial black holes. For now, they do not set limits, but it could be the case with better PTAs. LIGO could potentially place very stringent bounds on the abundance of primordial black holes between a few and a few hundred of solar masses. But this depends on whether these binaries formed in the early universe could or not be disturbed during the formation of the first structures in the universe. That's something that's under investigation. And I will stop here and take any questions, or if I'm a little bit late.
Thank you, Yacine. There are a couple of questions. Let me allow the participants to ask the questions maybe directly.
Okay.
Just bear with me. Professor Bhattacharjee, would you like to ask the question? Can you allow? Okay.
Yeah, I was just. Anyway, I was.
Okay, maybe I will read the question.
Yeah.
Is there any effect of dynamical friction on the merger rate? And if yes, is it taken into account in the estimates you had given?
Right. So if by dynamical friction you mean of, say, smaller primordial black holes or particle-like dark matter, yes, there should be in principle have some effect. There should be in principle some effect. We try to estimate this analytically in this paper. We found that it should be small, but like all the other things we estimated analytically, this should be checked in simulations. So if there are, if there are primordial black holes which are mostly of some mass, but then the rest of them are, say, very small primordial black holes, or if the rest of the dark matter is in particle-like dark matter, then yes, this could lead to some dynamical friction on these binaries, and this could affect their merger rate.
So the next question is, for primordial binaries of primordial black holes, does one use the lower cutoff in separation from the size of the region which would collapse to form the individual black holes?
I see. So one should do this in principle, you're absolutely right. However, in practice, those are very, very separated scales. So the regions that collapse to form, so the time at which these binaries, maybe I have it here, sorry. The redshift at which these binaries form, typical redshifts are, a few tens of thousands to a few hundreds of thousands. The redshift at which the primordial black holes themselves collapse is much, 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 much before this. So as we estimated before, it was something like 10 to the 11, if I got this correctly. So the horizon size at formation versus the horizon size versus the separation of these binaries, there are very different scales. So you could have a cutoff in principle, but in practice, it's basically like zero. It's so much smaller than the mean PBH separation that it doesn't have, you don't actually have to enforce this in your calculation.
Okay. There is one more question, Yacine. As PBH binaries in early universe are dependent on the initial distributions, what is the most stringent constraint on FPBH if PBH binaries are the LIGO-Virgo candidates?
As they are dependent on the initial distribution. I see, you're asking, I guess, most conservative, the most stringent constraints. So I think what you're asking is whether the initial clustering of primordial black holes, if at all, could strengthen, could make the merger rates larger or smaller. And I haven't worked on this myself, but I know that there are a few papers which I think might get contradicting results. So I don't think it's an easy calculation to be done. And I don't have a clear answer for you. If primordial black holes were clustered beyond Poisson, it is not obvious whether this would increase the rate of merger, because naively you think, okay, they're already closer. But it could also decrease it because you can circularize these primordial black hole binaries because the others have a stronger torque. So it's not obvious which way it goes. So I don't have an answer to this question.
There is one more question. It says, in your paper, merger rate of primordial black hole binaries, you took this approach, the approach by Professor Nakamura.
Yes, this paper, That's right. This paper redoes this in a more accurate way and more precise way with, and also checks analytically whether these early universe binaries could be significantly torqued by the formation of structure. And in this paper, we also revisit the Bird-et-al merger rates. So this is trying to recalculate both early and late time scenarios in a more accurate way.
There is a question by Professor Bernard Carr. Professor Carr, can you ask the question if you're...
Yes, indeed. Can you hear me, Yacine?
Absolutely.
Yes.
Well, welcome from England, first of all. My question is about the nanograv detection, observations, which you talked about. Now, there have been some recent claims, in fact, by 4 groups. I think there's Corian Terada, De Luca et al., Vasconen, Vermeij, and Dominic et al., who claim there is actually evidence for a signal, and they've even claimed to get a sort of mass scale and dark matter fraction associated with it. So, but you didn't comment on that. So I wonder what your opinion was of those claims.
Right. So my understanding is that these papers say if there is a signal, it could be consistent with this the correct mass scales, as you were saying. The point I'm making here is that there is no signal. So I'm taking one step before. I think these groups may not be very familiar necessarily with what goes on into the data analysis of pulsar timing arrays. And I think also the nanograph collaboration perhaps presented their, this bump in the autocorrelation noise in a way that could lead people to think that it's a hint of a signal. Nevertheless, it is not a signal. The signal would be only, something that would prove there would be a detection of gravitational waves is if you could find some signal in cross correlation between different pulsars. That is unambiguously gravitational waves. If you just find a signal which is in autocorrelation, well, it's not the gravitational waves. So it's some sort of noise, but it's not gravitational waves. We don't know what it is.
So if there's no signal, are you saying that claims are wrong, essentially?
Well, I'm saying that the interpreting this bump, even if you read the nanograph paper, they are very careful. They don't say that this is a gravitational wave detection. It's what they call a common red process. So that would be, imagine if all the pulsars have some similar noise processes, you could, tuck in some red noise, which is common to all of them. Okay, and so this is what they detect here. They say all pulsars have some common red noise in their autocorrelations, but this is not correlated between pulsars from different pulsars. Otherwise, you would see it also in this blue curve. So the fact that it's not correlated, it means that it's not gravitational waves.
That's very interesting. So essentially, they really got up a limit rather than
They got a limit. But they, are Nanograv is presenting things to try and, I guess, keep people's interest by emphasizing this common red process, which they think could be a hint of gravitational waves. But yes, it's I think it's a hint that the data analysis should be done a little bit differently. That's my personal point of view.
Thank you.
You're welcome.
Thank you, Professor Carr. There are a couple of other questions, Yacine. Yeah.
And I'm happy to take questions, but I don't know.
Let me just understand from the host. Can I take 1 or 2 more questions?
Maybe one question
Okay.
we can ask by email.
Yacine, maybe we can have one question. Okay. What possible processes could disturb the PBH binaries after their formation so that it could change the constraints?
Right. So the simplest one that we want to investigate is, okay, I'm going to show you again these plots. Okay, so this is, Jedamzik will probably talk about this. So if you have here, you start with some binaries. It's really hard to really read these plots. It's pretty, but it's hard to read them. You start with some binary and you have a third primordial black hole. So say you have your binary that formed the early universe and then structure forms around it, as in these simulations here. Right? So these are primordial black holes. And then as time goes on, the random particle fluctuations will lead to the first halos of primordial black holes. So now if you imagine that one of these point masses here actually is a binary, and then you have a third primordial black hole that comes in, it might interact with this binary, and it could just torque it a little bit, or it could significantly torque it, or it could even exchange, one object with the other and completely, disrupt it. In that case, obviously this binary would not merge at the present time.
Okay, let's thank Yacine for the 2 lectures. I'll applaud on behalf of everyone, Yacine. Thank you very much.